I see. All right. There, I think we're good to go. It's time to play Let's Make a Deal, folks. Can you guess what I'm going to say about this? What am I going to say about this?
Do your course evals, please.
Yeah, not just please. First off, the other class is beating you, and that's unacceptable. Up to 2 bonus points. So here's my deal. As usual, per semester, my goal is to have as high of a response rate to my evaluations as possible so that I have as representative of a sample as possible. And what better way to have a representative sample than to get the population? So the 20 of you are the population for this class. If at least, let's go with 18 this time. If at least 18 of you complete a university course evaluation by Saturday night when they close, everyone gets a point of extra credit. In addition, this morning I configured a Qualtrics survey that I use to collect additional feedback about your experience in this class with more targeted questions. You'll receive an email this afternoon with an invitation to complete the survey for this class. Everyone who does gets a separate point of extra credit. So that one is just for you. The way that it works is that I feed your email addresses into Qualtrics, and I can download a spreadsheet that says whether or not each of you has completed it, but your survey responses are not connected to your email. So it is anonymous in that sense. I don't look at them until I get all the way through the semester and I get all the course evaluations back in one day. So you don't have to worry about that. But I do want to know what you thought about things since I tried some new things this semester, the projects in particular. The written assignments are also somewhat new, so I'm interested in how your perceptions of those were. So yes, up to 2 bonus points. The due dates for this, the university course evaluations, which you complete through Icon, I believe. Is that where you get them from? This is where I'm at anyway. Those are due Saturday night. You have until the end of finals week to do the Qualtrics survey. So this one needs to be done first, and then the Qualtrics survey will be done. You'll have another week to complete that. So that's my deal, folks. As you can see in semesters past, usually the deal is pretty effective. But no one has beat the semester of fall 2020 when I had 2 100s. So let's see if we can do that again. It is a common misconception that only people who really hate you or really like you complete evaluations, and I would like to prove them wrong by getting as many evaluations as humanly possible. The way that these are used, by the way, the numbers go into my merit evaluation and my 5-year review packets. They're more important for junior faculty who are up for promotion and tenure. The qualitative comments are useful for contextualizing the numbers, but what you like and what you didn't like are not specific enough questions for me to be actionable in most cases, which is why I go to the trouble to collect the Qualtrics survey that has more specifics. So I am interested in your opinions and willing to compensate you for that. So that's my deal, up to 2 points extra credit. Any questions on that? All right, then I will shut this. Let's see, things that are happening. This is the last week of classes. Happy Garbage Day, by the way. The last time I get to wear my merch this semester. Unfortunately, it's still cold enough that a long sleeve shirt has called for, even though it's May. Such is life in Iowa. You have your last homework assignment that if you want feedback on it before it is due for real, you can submit by the end of the day Friday. And I will try to get to that. I'm hopefully to get them all graded not by Monday or Tuesday of next week. And then if you want to make any revisions for additional points, you can do so. If you don't have time to submit a draft of that this week, that's fine. Just make sure that you get it in by the end of finals week. And any other outstanding work needs to be finished by the end of finals week as well. I will update grades, let's see, tomorrow morning because we still have folks who are turning in their peer reviews of projects. And so then I can accumulate all of those points and make sure that I've caught everything. But otherwise, I think I'm caught up on grading. Maybe? For one brief shining moment, I'm caught up on grading until more stuff comes in. So, any questions or things that I'm forgetting? No? We're good? Should we talk about 3-level models then? Why not? I figured this would sort of not only round out this class, but also serve as a segue for those of you who are interested in learning more about multi-level models in the group context. So the theme here is 3-level models incorporating people who are nested in groups. And the way that that is formulated depends on the type of sampling design. So I'm going to start off with talking about just some different types of designs and how the levels would be configured in those cases, and then focus on the context of what is known as clustered longitudinal data more specifically, which is when people who are followed longitudinally are nested in groups, and the groups are time invariant. So the example that I have for you, the octo-twin data, as you've seen several examples, we're finally going to do the twin part. That's the goal here, because as it turns out, people who share genetics are not independent. Who would have thought? All right, away we go then. So 3-level models, random effects for longitudinal data, making sure that I'm recording. Okay, good. So what are your choices in terms of how to address the contribution of people when they are nested in groups? You don't always need to make it another level. So the choice is basically whether to control for group membership, the nesting of people in groups, the dependency of people in groups, however you want to phrase it, as a model for the means fixed effects strategy versus a model for the variance random effects strategy. So fixed effects, and that is what is known as fixed effects modeling in some disciplines. They use the term in the same way. You would literally treat group as a categorical predictor with respect to group ID. So that would involve estimating as many slopes as you have groups, minus one for the intercept. And if you do that, then group or cluster, as I'm calling it here, is not a level. So the simplest case for this would be, what if I have a longitudinal intervention study where some people are in a control group and some people are in a treatment group? Well, once you put in which group you're in, you're done, right? There's only one slope that is needed to differentiate group membership. So even though people are nested in clusters or groups, you don't need to bring that into the model as a level. When you would need to do that, though, would be something like if you had multiple sites involved, and let's say that you have 10 control sites and 10 treatment sites, then just that one dummy code for treatment versus control is not enough. Because it may be that people who are from the same control group or the same treatment group are more alike than people from different groups. So there's more to the story then, and that is when you need to worry about this. So in that case, if you had 20 different groups or clusters, you would put in 19 dummy codes if you wanted it to be a fixed effect. Now the benefit of that, you're controlling for cluster dependency or people nested in groups just fine. If you are interested in making inferences, so like if you have, the Tennessee site versus the South Dakota site versus the Iowa site, and you want to talk about outcomes specific to those groups, doing that as a fixed effect is the most useful strategy. If you don't want to do that, then that would be where you turn to the other side. So if you're interested in the specific cluster comparisons, or you don't have that many, then putting it in as a fixed effect is probably sufficient. Where it would be necessary to make it a level, meaning add some kind of random effect variance for it, and intercept at a minimum and potentially slopes as well, is if you want to predict why the clusters differ from each other. So why were some sites more successful in their treatment? What characteristics of the site led to better outcomes? If you want to answer questions like that, then we need a variability component across the sites that those types of predictors could then address. So this is a better option if you have a lot of different clusters or if you want to predict them. But keep in mind that your power to do so is predicated on the number of clusters. So I have really bummed a lot of people out with this idea. Like if you have a randomized control trial where the cluster is randomized. For instance, I worked with the PI who had access to like all the students in one school district and had like 13,000 students or something. And they were going to have 5 control schools and 5 treatment schools. And they thought they had plenty of power because they had 13,000 students or whatever. And I'm like, no, you don't. Your power is 10. Because at the level of the randomization, it's 5 and 5. So more people can't help that because within a school, the group they're assigned to is a constant, not a variable. So your power to detect cluster differences depends on the number of clusters you have. If you don't have that many, you're probably better off trying to make them fixed effects instead, because trying to estimate a variance across 10 units is not going to go well. It's going to be very unstable, likely lead to non-positive definite covariance matrices and that kind of thing. So we're dealing with the situation in which you have either enough units or you want to try to predict differences between them. That would merit a random effects model. So thoughts or questions on that idea? Yes, Carl, I see your hand up.
So if I'm trying to remember stuff that we've talked about briefly for intensive longitudinal data, this is like similar thing where we have 3 levels. It's just that we have like occasion, burst, person, or something like that, as opposed to like a different sorts of maybe like school or twin clustering.
It's another level, but it's not necessarily 3 levels. It
Okay.
could be 2 units crossed at the same level based on the sampling design.
Okay, not necessarily 3 levels, but
Not
it
necessarily.
could. So like, but you had if you had persons, work groups, and then like multiple observations of people in work groups over time, like that would be a 3-level design.
That would be
that you
that
could
would be
represent
3-level
with.
nested. Yeah, if they stay in the same group all the time, then people are nested in groups and occasions are nested in people. But if it's
Okay.
something like the kids move classrooms, like at time 1 they're in this classroom and time 2 they're in the next classroom, then it's not 3-level nested. It's actually 2-level crossed instead. But there's another source of variability due to cluster either way, and I think that's the important consideration.
Okay, got it. Just making sure. Good.
Yep. Thanks for the question. Other questions or thoughts, comments? So how do I know? Woo. Okay, no questions. Bye-bye. Or my internet just crapped out, one of the two. Right? So what determines the number of levels is a common question that I get, and the answer is the outcome only. So Y determines the number of levels, not X. So how many dimensions of sampling do you have with respect to the outcome to be predicted? So the example that we have here, let's say that I have longitudinal data and I have 1 person per family. So I'm studying child outcomes or parent outcomes, but there's only 1 kid and 1 parent, right? So if I think about it that way, it's just a 2-level model. And I can think of these as observations within families or observations within people, because people and family are the same thing. If I had a study where I have either couples or maybe siblings, where there's multiple people per family, then that's a 3-level model, because you're in the same family all the time. If you have this sampling design repeated across multiple cities, then that would be a 4-level model. But either way, it depends on where the outcome is measured. If it's measured per occasion, then that's where you would have time as a level. So the sampling dimensions can be crossed instead of nested, if that's possible, or they could be modeled with fixed effects, which would reduce the degree of nesting. So what this means when you say you're going to add a level is that you're adding a set of random effects. And the rule is random effects are correlated at the same level, but not across levels. So like I could have a person intercept and slope, and I could have a family intercept and slope. And the intercept and slope from the same person would be related, from the same family would be related, but the person one can't be related to the family one. So a level is like an orthogonal set of variance components with respect to this. So here's some example 3-level designs demonstrating that time is not always level 1. And all of these I have seen in either workshops or classes before as examples. So here's an example from country research. So this would be like maybe sociology or political science or something like that. If we're predicting occasion-specific respondent outcomes, so it's all the same people in all the same countries measured over time. So then level 3 would be countries, level 2 would be respondents, and then level 1 would be occasions. And so this would be considered clustered longitudinal data, is the words that would go along with the sampling design. So in terms of time varying predictors, in this design, they could happen for countries or they could happen for people. So there may be things like a country's GDP or other acronyms that describe its economic output in a given year. In that case, that variable would have variability at level 1, and it would have variability at level 3, but it would skip level 2. If it's a country measure that varies over time. So then logically speaking, you would have potentially the effect of having more or less of that than usual at level 1, and then at level 3, the effect of coming from a country that has more of that than other countries tend to have. But it would skip level 2. Likewise, for people things could be at the people level, obviously, but they're also potentially at the country level. So if you have something like education level, countries may differ in the average education level of the respondents in the study, and that becomes a level 3 characteristic in addition to a level 2 characteristic. Random effects. Things that are time specific, such as what year it is or any other time varying predictor, could have a random effect across people, could also have a random effect across countries at the same time. So that's the extension that we're going to be talking about in this unit here. Here's another one. This was a student who came to my longitudinal class because he thought he had longitudinal data, and he was mistaken. This is a 3-level design involving time, but I would argue that it is not longitudinal. What he had was a collection of survey outcomes. He was from the Survey Research Methodology group at Nebraska, where they had several years' worth of surveys that he was interested in. And within each year, they had a set of interviewers. And within each interviewer, they collected data from multiple respondents. But as years went on, it was entirely different interviewers and entirely different respondents. So year is at the top. I would argue that this is not longitudinal because you can't see how things change over time if there's literally no commonality across years in any of the observations. So you would have to make a really strong argument that whatever sampling strategy that you use to get your interviewers and your respondents is comparable over time. So in a design like this, its time is at level 3, interviewer is at level 2, and respondents are at level 1. So what would you do with years? You could do 2 choices. One is just to treat it as a fixed effect. So if you only had, say, maybe 5 years worth of data, then you could control for which year is which, and you're done. That would be the same idea as like treatment versus control at the top, and you just control it away with fixed effects and you're done. If you had a lot of years, maybe 30 years of data or something, you might want to treat it as a level, in which case you would estimate a random intercept across years that would address the potential for time-specific differences in whatever outcome you're measuring. So he was interested in particular with compliance, basically like how effective the interviewers were at getting the people to answer all the questions. So it might be the case that in some years, compliance rates are higher than in other years, but we don't know why that is. So you could look at things that were happening, like what was the state of the economy in that year, or how much did they pay the survey respondents in that year, or what kind of training did they give the interviewers in that year, like that kind of thing. So if you're interested in predicting why some years had differences relative to other years, this would be random. If you just want to control for which year is which, and you don't have a lot of them, that would be fixed. So he made it through the class, but I'm like, yeah, dude, you don't have longitudinal data. You have clustered data, really. Like, this is how I would think of it. It's clustered. It's not longitudinal. Okay, with me so far? Okay. Here's another one. I came across this type of design when I was teaching workshops for ICPSR, the Institute of Michigan, which, by the way, is how I paid off my student loans. So once again, quant makes you money. So I did that for a few summers until my loans were paid off, and then I gave it to my graduate student after he graduated, and he did it for several summers until his loans were paid off, and then I don't know who's doing it now, but it's not me. So anyway, folks who came to those workshops tended to have designs that looked like this. This is from political science in particular, where they had longitudinal studies of countries, and the way that they did it was countries were repeatedly measured over time, but at each occasion they had different respondents. Yeah, that face, that was my face too, like, what? So in this case, they were interested in seeing how countries changed over time via the responses of individual people and different people in every years. So that made me feel, my word for that is squishy, which is sort of my word for uncomfortable. You have to really be willing to believe that whatever processes they gathered respondents were comparable across years before you could say that, like, this is the same country across years. But if they were willing to say that, then Godspeed. So they would have an example that looks like this, where we have respondents at level 1 nested in years, which are nested inside countries. In this case, so time is level 2. And so then a question I would get from them is, well, once I put in a dummy code for which year is which, does time stop being a level? And the answer is no. So if you think about it from the perspective of how countries can change, if I put in a dummy code for whether it's year 1, year 2, year 3, and so forth, what that does is allow for systematic mean differences as a function of what year it is. But I still have the potential that country 1 changed differentially in year 2 relative to what the average change was. So because countries can change or fluctuate differently than other countries, just controlling for which year is which does not eliminate this middle level right here. So this is, do I have a slide about this? No, I don't. Okay, I'm going to do it right here. This one. So here's the dirty secret that I've actually hidden from all of you up to this point. And since you've been with me for like an entire year worth of courses and it's the last week, I'm going to let you in on the secret. You know how I said that time is nested in persons like 8,000 times? I lied. Time is crossed with person. I know, I lied, but I had a good reason. Because we haven't talked about cross models in this class. That is one of the things that we're going to get to in the clustered class, because without time, I have like 8 weeks of material that I can make room for, because time takes up a lot of time, no pun intended. So as a backstory to my explanation here, I will say that the Quantitude podcast, so T, I'm finally going to tell the story that you brought up like 3 months ago. I remembered. It wasn't relevant yet, but now it's relevant. So on the Quantitude podcast, which is Greg Hancock and Patrick Curran do this podcast that I listen to and many other people listen to. I've known them for a long time. And they asked me to be a guest star on their Christmas episode, which they did this sort of holiday episode of pretend employees who were disgruntled about having to go back to the office. And so we were supposed to ask really difficult questions, like to put them on the spot. So they asked me to submit a question and to record it, and I did. And my question was, why is it that we talk about time as nested in person when in most cases it's actually crossed instead? That was my question, because it is a tricky question to answer. And so I submitted this question to Greg, and a couple of days later, I get a text from Patrick that was basically, WTF was this question mean? So I'm like, do you want me to like send a new question or try to explain? He's like, no, I'll make it work. So he gave this answer that was, it was very creative. He was talking about vertical nesting. At one point he talked about diagonal nesting and horizontal nesting. It was hilarious because he did not know what I was talking about. And so I maybe didn't phrase the question well enough, but I'll tell you what the secret is. So if you think of this from an experimental design, like think of it as like a two-way experimental design where I have people one way and I have occasions the other, time 1, time 2, time 3. That's crossed. Like I could legit think of people nested in years just like this, or I could think of years nested in people. And if you can think of nesting either way and it makes sense to you, that is your clue that it is not nested, it is crossed. So every observation is a function of who the observation is for. So a random intercept for person at a minimum would move the mean up or down. What occasion it is would also move the mean up or down. and then some kind of residual for why that person's occasion was different than was predicted by those two main effects. And if each person is only seen once at an occasion, you can't separate out that person by time interaction variance. So the reason that I lied to you was because time is nested in person once you put the fixed effects of time in the model. So once you control for the change over time on average, either as a saturated means model or with, say, a linear function or a piecewise function or what have you that adequately recreates the means, then occasion mean differences are no longer across dimension. They go away, and all you're left with is the level 1 residual person by time interaction that we sort of abbreviate as time within person. So that's the dirty secret. I lied to you. But that's because I didn't think like that would help to tell you that up front. So if you're not going to put in fixed effects for which occasion is which, or try to predict mean differences, an alternative would be to have a cross dimension that is a random intercept for time. And that would make sense if you have an intensive longitudinal design where you have many, 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 many occasions. Then each occasion could have a different mean for whatever reason, and you could use fixed effects to say why that is, but still have variability left over. So time is crossed with person. It becomes nested. The cross dimension goes away once you control for which occasion is which by fixed effects. So that's the official answer that I was going for on the podcast, and I'm giving to you now. And there's a couple paragraphs about this in chapter 11 of my book as well, when I talk about time-varying groups being crossed instead of nested. Can you forgive me? Yeah, it's actually crossed. So this makes more sense in the context of persons and items. So if you have a person who responds to repeated measures in the form of item responses, then like a given response is a function of who answered the question and which question it was. And so to the extent that some questions are harder than others, that's a random dimension. To the extent that some people are better at answering the questions than others, we'll call that ability or whatever, that's a dimension. You can either control for which item is which would be like a psychometric model where each item gets its own intercepts, loadings, residual variances, thresholds, whatever you need, then that dimension goes away and items are nested in people. Alternatively, Nathan, this one's for you, you cannot do that and have items be a separate crossed random dimension in which item difficulty is the random intercept. So items can still be more or less difficult from each other. The latter, making it random, would allow you to predict why that is. Not just give each item a separate difficulty and discrimination, but predict why they need to be different. So crossed designs tend to be more common, I think, than folks realize. It's just a question of whether it remains crossed or whether you've controlled for the cross dimension via fixed effects. So fixed effects of items or fixed effects of time, move it back to a strictly two-level nested situation instead. How's that? Okay, questions, thoughts? All right, moving on.
I have a question, Lisa.
Yes, hit me. Figured you would.
So, crossed means that everybody, so like all of the indicators or variables, whatever you want to call them, in the level above share, or there's some sort of combination of the lower level variables going on. I don't know how to say it, I guess.
Yeah.
You know what I'm trying to say?
I think so. Like I picture like a grid. And if you can have like a row and a column and there's like everyone fills out the cells, like that's crossed, not nested. Nested would be like if only certain occasions were for certain people, which can happen in unbalanced designs. Like at the extreme, each person could literally have their own set of occasions, in which case there is no common set of occasion mean differences that are possible to evaluate. But in most designs, it's at least reasonably crossed. Yeah, go ahead.
So When we say that something is nested, we're saying that time one for person one is independent from time one with person two.
Yes, it is
Okay.
after you control for the fact that it's time one.
Okay, that makes
And
sense.
you can do that as a saturated means, like literally control for time one versus time two, or you can do that with a function that captures those mean differences instead.
So would it be better to say the residuals at time one for person one are independent from the residuals from time two with person, or time one with person two?
Yes, you can say that.
Okay,
Yes.
thank you.
Yes, so then person by time really is what level one means, because it's the unique time observations after controlling for the main effects of time, so to speak. And you have to have more than 2 occasions to be able to differentiate person by time from random slope variance. If you don't, then it's the same thing. Okay. So then in this design here, back to countries for a moment, where year is level 2 and respondents are level 1, this is presupposing that the outcome that we're trying to predict is a person characteristic. Like a person answer in a given year from a given country is the outcome. Then this would be my 3-level model. But what if what we wanted to predict was a country level outcome in a given year? Then, if that's what we have, we don't have a 3-level model anymore. If the outcome you're predicting is per year per country, the people have nothing to do. It is not a 3-level model at this point. You have a 2-level model in which the only way that people can contribute as a predictor is in the aggregate. You would have to somehow aggregate the responses in a given year and use like the mean of that year as the predictor, or the range, or the variance, or some kind of summary measure of the people responses in that year, because there's no individual outcome for the people responses to predict. So this is a 2-level model. So we could have time-specific averages of the respondent predictors, which would account for time level variation. We could also have across time country averages of the people information, which would go up here at level 3 as a predictor instead. All right, that's enough of that. Oh, equations, fun. I know, said no one ever. So these are just some samples of possible designs involving time. The punchline to this is time is not always level 1. What your levels are and whether they're nest or crossed depends entirely on your sampling design and how you're going to set up the model, because some of these things can be collapsed if you estimate fixed effects rather than random effects for that sampling dimension. Moving forward, I have focus on clustered longitudinal designs with 2 brief asides related to intensive longitudinal designs and then related to time varying groups within the slide deck here. Got a question: if a level is fully crossed, can the relationship among variables within that level be expressed via correlation covariance? I'm not sure I understand the question.
So, like, if you don't, I'm still kind of stuck on this. Like, if you don't control for the effective time, then the lower level, like, the indicators are all going to be, like, they're all sharing. They're not independent. You know, they're sharing time. So, like, could you, like, through like an alternative covariance or some sort of covariance structure, could you model it that way instead of like specifically identifying the effective time? I don't know if this could just also be because this is the first time I'm looking at this too, so it might not make sense what I'm saying.
You could allow correlation among the residuals, but that wouldn't solve the problem of systematic mean differences across time being a separately differentiable source of variability.
Okay. Okay, so you could say like time 1 for everybody, but you wouldn't be able to say time 1 for each individual.
Yes?
It was fully crossed.
Maybe?
I'm gonna have to think about this.
Yeah, me too. Me too. Usually what we do is control for mean differences across occasions via fixed effects because there's not that many, but an alternative is a random effect in which time becomes a cross dimension at level 2. That's your take home point for that. All right, so clustered longitudinal then. Here is what a 3-level equation would look like, and boy is this ugly. I will share that it took me, oh boy, a long time to get this right. So for those of you who are doing 3-level projects and attempting equations, Godspeed. Good job trying, because this was really hard for me. The idea here is that there are 2 different kinds of placeholders being used rather than one. So I have decided to change from TIJ or TIG for group into TIC for cluster, and I'm slowly moving all of my slides to have C's in them. So the notation here is T is for time, I is for level 2 individual or person, and then C is for cluster. So this would be appropriate for multiple children from multiple schools measured over time, or multiple children from the same family measured over time. The example that I have is time within twin pair. So this would map onto that as well. This is an empty model. Here's the composite equation. That might be a little bit easier to understand. Because I have 3 subscripts here, TIC, I have 3 everywhere else. So this is still gamma 0, 0, 0, that's my fixed intercept. Given the 3 levels here, this is the mean of the cluster means. Then I have V, and I say, my bad. Because when I was trying to come up with notation for this, my brain literally went, well, if U is level 2, what comes after U? TUV. Okay, V is next, right? That's going to be level 3. And then I did that, and then like 3 years later, well after the book was published, I get a question like, is that the V matrix? Oh, shit. No, it's a different V. So I'm going to need a new letter for level 3 from now on. Any recommendations? TUV. W. Yeah, should we do W next time? I think I used W for something else maybe, but I need a new thing for level 3. Other books use U but then change the subscripts, which I don't like because it's just too hard to keep it straight at that point. Like, I need something that's visually different. So sorry for using V. I honestly did not realize I had reused it, even though I totally should have, so my bad. So V, because it's after U, is level 3. So like this is the idea that some clusters are higher on average than other clusters. So like it starts with what's the overall mean, then what's the bump from your cluster, and then once we get to your cluster's mean, then U is the deviation relative to your cluster. So if you are higher than the rest of your people, your U is positive. If you're lower, your U is negative. So between person differences, as we're used to thinking about them, is a combination of these 2 things. Between person is what group you belong to, and then your relative position within that group. And then E is, once you get to your own person mean, E is how far off you are at that particular occasion. So there's 3 different variance components, 1 at each level. These are orthogonal because they're at each level, which means we can add them up and come up with the sum. And the easiest way to describe this, I think, is literally to sum these and then compute the proportion at each level. So that's what I would do, like for transparency's sake, and then you can use those proportions to come up with various kinds of interclass correlations that we'll talk about. So that all seems reasonable when you put it into this composite. How you get there from the placeholder notation is more complicated. So if we start with an outcome, TIC, we have our beta placeholder like usual, E like usual. Then level 2, our beta placeholder is defined with another placeholder. So this is delta, I think, lowercase delta. Why is there an equation in my chat box?
I did a search for like notations for level, the
Okay.
3rd level, and they use pi's and betas apparently.
Yeah, okay. All right, so delta placeholder here that then gets defined at level 3. So question from the Zoomers, Carl.
Sorry, I don't know if you said this briefly, but I'm looking at 4 parameters for this empty model, right? 1 for the means and then 3 for the variance.
That is correct. Please change this 3 to 4.
Okay.
Thank you for finding my typos. This slide is at least 10 years old. I changed all the C's, but I can't count. So, Thank you. Yes, 3 variance components and 1 fixed effect, so 4 total parameters. But the new complexity here is that this delta thing is a placeholder for what happens at level 3. So then finally the fixed effects show up at level 3. So the delta OOC is how each cluster gets its own mean. It starts with the average across clusters plus yours. Then that populates down into level 2. We pick up the deviation for who you are relative to your cluster. That populates down to level 1, and then we pick up the E for which occasion it is. And the gamma OOO fixed intercept will not be the same as just the mean of the variables if you don't have an equal number of people per cluster and occasions per person. So the unbalance of the data will create a weighted mean instead. So it would be a little bit different depending on how many levels you have in your analysis.
Lisa?
Yeah.
So now in our G matrix, we will have 2 random variance terms, right?
Yes.
For the 3 levels. And if these are orthogonal, the covariance is 0 in this case.
Yeah, so the G is now like a block diagonal of like the level 2 stuff and the level 3 stuff. And within the level 2, you have covariances, and within the level 3 you do, but then across you don't.
Okay.
So you can see that explicitly if you ask for the G matrix in SAS, it will show you that like block diagonal structure. I'm not aware of but showing it that way in other packages though.
Great.
But chapter 11, by the way, is where this content comes from. I have that in there. So in terms of partitioning variance and where the stuff comes from, I feel like that's useful to understand what kinds of ICCs would be useful to describe and it depends on your sampling design. But if we have this example 2 level from without clusters, so once upon a time there was an E. The first thing that we do is split E into how much is level 2 versus level 1. So then we have between person intercept variance, and the interclass correlation we would compute is how much of the total is due to level 2 between. How much of it is cross-sectional as opposed to E, which is longitudinal. So then, if we change this to 3 level, and note the change in the color, I've got green in here is for shadowing, instead of just the 2 blues, right? That's deliberate. So now once upon a time there was an E. First step, same thing. How much of what we're calling longitudinal variance is actually cross-sectional due to between person mean differences versus longitudinal E? So I'm calling this ICC level 2. That's your first partition, that's the same as usual. But as you can tell, this is a hybrid still of two colors because to the extent that people are nested in clusters, people from the same cluster may be more related in their outcome. So then the next question is, how much of what we're calling between person mean differences is actually due to the cluster they're in? So to answer that question, we take what was level 2 and we split it into 2 versus 3. So this is important. It's not E. E is the longitudinal part. Level 2 is cross-sectional. We're taking the cross-sectional part and splitting it into how much is clustered. So that gives a new interclass correlation where the denominator is the person intercept variance at 2. How much of what we were calling 2 is actually 3? That's ICC level 3. So then ICC level 3 is your effect size for how much dependency you have because people are nested in clusters, irrespective of time. So time is not in the computation for this. So we're at this point then where we would have a level 3 intercept that comes from the level 2 intercept. So then it's between cluster versus within cluster, and then we have within person at the bottom. So what you call level 2 is up to you. You could either call this within cluster or you could call it between person. Anything that's an intermediate level could be either a between or a within, whereas level 1 is within person, level 3 is between cluster. So level 2 is ambiguous in terms of what you would call it. But if you want to talk about how people differ from each other, that's 2 and 3 together, because people are from groups. All right, so here's the equations that go with that. And I will apologize that in the equation editor, it looks like it's between minus person. That's a dash. It wouldn't let me have a short dash for some reason. So, and you know how picky I am about my dashes. Like, that really bothers me. But I couldn't fix it. So this is between person, not between minus person. So ICC level 2 is conceptually the same thing as what we called ICC before. It expresses the correlation of occasions from the same person, where the numerator is the level 3 variance plus the level 2 variance divided by the total of the 3 levels. So the V and the U, level 3 and level 2. So this is how much of your total outcome variation is cross-sectional is due to between-person differences. Between-person mean differences, specifically. Then the new one is focusing on breaking down the numerator of ICC level 2 into how much is 3. So note that the time level 1 variance is not in here anymore. It's of what we called between-person cross-sectional, how much is actually due to between-cluster differences, and that's your numerator. So this ICC tells you the expected correlation of persons from the same cluster, irrespective of time. The likelihood ratio test that you would get for adding level 3 to your model is the significance test that goes with this effect size interclass correlation. So explaining this gets tricky, but the way that I would typically approach it is of the part that's between persons, how much of that is between clusters? It's not of the total, which is what the first one is. Okay, with me so far? Here is an alternative version that is more useful for intensive longitudinal data, such as T's project, where you had occasions within days within people. Do it this way instead. So once upon a time there was an E, and E is composed of within day variation. So if you measure cortisol 4 times a day for multiple days for multiple people, then the first thing that I would do instead of splitting 2 and 3 off is to split 3 off. Because you have 2 levels of time, and the top level is person. So the first one is like how much of the total variation is cross-sectional is due to level 3. So conceptually it's the same idea, it's just implemented in a different way given the difference in design. So E variance at this point is 2 and 1 shoved together still. It's just time within person, and we're not paying attention to whether it's different days or different occasions. So how much of it is cross-sectional? Then we can take the time part and see whether or not there is a need to distinguish which day it is. So I'm breaking down what was 2 and 1 put together and seeing how much of what I was just calling time depends on day versus within day. So this would answer the question, do I need a 3-level model where I pull apart occasions and days? If so, what that means is that occasions from the same day have a stronger correlation than occasions from different days. And so you need to account for which day it is. There are day mean differences that are causing this correlation. So then the interclass correlations that go with this are a little bit different. So the first one I call in the book level 3B because it is an alternative level 3 interclass correlation that is just level 3 over total. This is what is given by Stata and M+. Okay, it's this version. It is not really a correlation. It describes the correlation of any occasion from the same person, regardless of what day it is. This one down here that I call level 2B is because it's a level 2 relationship, but it's different than the one before. This is level 2 over level 2 plus level 1. This is how much of the time variation is due to which day it is, as opposed to which occasion it is within a day. So this is a different ICC process than what I would go through in a clustered longitudinal design. The moral of the story, can you guess what it is so far? Don't just say ICC. That's not enough information. I've already given you 5 of them, and we're only on slide 12. There's still more, actually. There's more. What I think is most helpful in designs with multiple levels like this is just first say, what is the proportion at each level? Because then your reader can make whatever ratios out of those they feel like 15% here, 50% here, 35% here. That is helpful to know just the proportions. But this is how I would do it to test whether or not I need to differentiate day as opposed to just occasion instead. All right. Okay, so these are just empty models, right? Want to make it worse? No, don't make me. Who would I be if I didn't make it worse? But first a question. Carl, go for it.
Sorry to keep asking so many
I like
questions. So I guess I'm getting a little bit hung up here. Is this just a different like model building order, or like how? I guess I'm just sort of confused on this idea of like, okay, so we have all of our time varying data at level 1, that's occasions.
Mm-hmm.
And then what you're saying here, I think, is the first like random intercept model that we estimate, it has person ID as the nesting, as opposed to day, right? As
Right.
opposed to like what's in between occasion and person.
Uh-huh.
So how exactly are we getting to this next step where we're pulling the variation out of the first E that we created with that model? Like where, yeah, I guess I'm just lost at what's going on there.
Okay, so you would tell your software basically what your levels are and what the ID level is that indicates your nesting. So the first level you'd put in would be a random intercept over people ID. And then the second level you'd put in would be a random intercept over day ID within person. And what that looks depends on what software package you're in.
Okay.
So let me try and explain this a different way. Each of these is based on the premise of the duh part first and then the question part second. Like if you have longitudinal data, no one in the world is going to question the need for a longitudinal model because the intraclass correlations, the extent to which occasions from the same person are related is way high usually. So like this is like, in this case, if I go back to clustered longitudinal, splitting out person from occasion is the duh part. Like of course we're going to do it that way. That's the simplest model you would probably ever entertain for longitudinal data. Then it's like, well, do I need to control for cluster? Then that's the question part. And you can control for cluster as fixed effects, or if you have enough of them, then you can see how much of your between person variation is at the cluster level. The answer is yes, you do, because even if this is 0, it may not stay that way as you explain variability and it pushes variance up the ladder. So it's the duh part and then the question part for this. For 3-level intensive data, it's the same premise, it's just the level at which the duh happens is level 3. So the duh part, of course, occasions from the same person are going to be correlated. The question part is, does it matter if it's the last occasion on Tuesday versus like the first occasion on Wednesday? Does it matter what day it is the question part. And this is going to be based on the type of outcome you're measuring and the rhythms that would happen to that. I don't know if that helps or makes it worse, but there are different strategies for different designs based on what makes sense. The extent to which you need any variance component is always an empirical question based on a likelihood ratio test, though. That's a commonality. Telling your reader what proportion of variance is at each level you end up with, always helpful. Building a ratio out of those proportions is up to you how you build it. But this is where it depends on software, like what you get. You have, like, just knowing, like, for instance, ICC level 3 is Stata NM+, is not the version that will help you distinguish to what extent people from the same cluster are related, for instance. That doesn't answer that question. Okay, question again.
Okay, so it's really just a matter of doing you do the model with person ID as a random intercept first,
Yes,
and then you add a day in your next random intercept model
yes, underneath it.
as another, and then you just do a model comparison between those two. And if the second one you had is better, then it's better and you need the third level. It's just in the same way we do everything
Yep.
else.
Yep.
Okay.
Yeah, and in the first example of clustered longitudinal, you'd put in the random intercept of person ID, and then the cluster ID would go over it as level 3 instead. Okay. Yay! You're like, no. How about slopes? No. Yes, slopes. What about change? Back to 2 levels again. Time within person. Because after you put in fixed effects for time, time is no longer a dimension and time is within person, and I'm not lying to you. So in 2-level models, after we put the intercept in, we put in fixed effects of time here. Then we could add a random slope for change over time, and it comes out a residual. So why are you off your line today? Well, maybe because I need a different line than everyone else. And once you give me my own line, then that is now a level 2 person characteristic that joins the intercept at level 2. So then we end up with multiple variance components that describe ways that people differ from each other. Intercept, change over time. E is why are you still off your line today, which is identified as long as you've got at least 3 occasions. There. Animation fail. There we go. Once this is in, I'm not lying to you. I'm only lying to you in the empty model. Okay, so here's the 3 level. This is where we left off. Clustered longitudinal. So level 1 is within persons over time. Level 2 gets split into what is between clusters versus between persons within a cluster. We add in the fixed effects of time, and we add in a random change. I'm trying to do better than slope because there's many kinds of slopes here. So person change and it splits. But guess what though? How many colors are in here? 2. Because to the same way that people could have mean differences that are attributable to cluster, people can have change differences that are attributable to clusters, and that splits also. So then at the end of the day, this is what you would have, potentially, is E is why are you off your line today? That's the same. Cluster intercept is why do some clusters have a higher predicted outcome at time 0? So why do they start off higher? Then within a cluster, why are some people starting out higher than other people in that cluster? With respect to change over time, why do some clusters have higher growth rates than others? And then why do some people within a cluster change differently than other people in the cluster? So when all is said and done, we have 1, 2, 3, 4, 5 variances, and then 2 covariances. So the covariances only happen for the random effects at the same level. The idea that we can take intercept variance and split it into how much is between clusters versus within clusters across people, and change variance and split it the same way, then gives us yet another kind of interclass correlation. So those are given on the next slide, but here's where they would show up. Of the total between person intercept variance, how much is due to clusters? Of the total between person change variance, how much is due to clusters? Those are your 2 new interclass correlations, potentially. So here's what this would look like as an equation if you had all of this going on. So I've picked up beta 1 as my time slope, just linear for the sake of demonstration here. That means that now that I have 2 betas, I need 2 level 2 placeholders. So beta 1 is a level 3 placeholder plus a random slope. The level 3 placeholder comes down here, picks up the fixed slope plus the random slope at level 3. Putting it all together, and I think I counted correctly this time, 1, 2 fixed effects, 3, 4, 5, 6, 7, 8 with the covariances, and then 9. So hooray for me, I can count. I find it sort of funny that none of these intra-class correlations faze me, but I can't count from 3 to 4 accurately. We call that specific intelligence, maybe, or lack thereof. But this is the general put back together again, which I think is more transparent. Your intercept is a function of what happens on average, plus how your cluster does, how you are relative to your cluster. Your slope is a function of what happens on average, plus how your cluster does, plus how you are relative to your cluster. Yeah, okay. Good. Questions? And don't be shy, because it gives me a chance to suck on my soda. Back to 7-Up today. I've already hit my limit of caffeine. So this is a lot, right? Can we agree on that? But it's not new concepts. It's just an order of complexity higher than what you're used to. When I first tried to learn this, I was lucky enough to have attended a workshop at the University of Kansas when I was a graduate student. We brought in Don Hedeker. You've heard me talk about him. He's one of my personal heroes. He will be here in October actually giving a talk at SMEP. He's getting our Lifetime Achievement Award thing, and so he's going to be here, and hopefully his band is going to play as well, so it's going to be fun. His band is called the Pokaholics. But anyway, after the workshop, we had the next day, he was around town, we had him come to our work group meeting, and I asked him about 3-level models because he had talked about them, and to me it was like, how is this not redundant to have a slope at the person level and the cluster level? And he picked up a marker, turned to the whiteboard, and he drew this picture. So I credit him for making the light bulb finally go off on my head as to how it's not redundant to have random slopes at both levels at the same time. So if we focus on the blue lines first, and how the blue lines are being partitioned in terms of their variability relative to the mean slope here. This would be a 2-level model. So if I think about I have a mom and a dad here, and it looks like mom is growing faster than dad, but they're both growing faster than everybody else. So if I think about the difference between each person's slope relative to the mean slope, right? Like this slope is, here's a difference of 0.5, and this one's different by 1.5. Then this is a 2-level variance partitioning because it's just your slope relative to what happens on average without paying attention to where you belong, what group you belong to, what family and whatnot. A 3-level model does it differently. It first goes from the mean slope to this dashed line here, which is the average of the family slopes. This is the slope across the 2 people on average. So then the distance between the fixed to the cluster average, this dashed line, that's your level 3 random slope. From there, then level 2 is these little differences relative to your cluster average. So then mom relative to the cluster average has a higher slope, and then dad has a shallower slope. So it's not redundant because what it's doing is taking the full distance and just cutting it up into pieces. So then this illustrates, I think, whether or not you would need a slope at each level, that only makes sense to the extent that there is a commonality of the slopes from the same family. If one of the red lines were up here and one of the other red lines were down here, then it wouldn't help to have a level 3 slope because they have nothing in common. So it is possible to have a slope only at level 2 that's random, which would mean that people need their own rates of change, but people are independent with respect to their rates of change, that there's no correlation of the slopes from the same group, the same cluster, the same family. So it is reasonable in some contexts that you would have a slope only at level 2, people differences, but there's no commonality of the change of people from the same clusters. If you had a random slope at level 3 only, that would be unexpected. In this context, what that would mean is that clusters change differently, but everybody from the same cluster changes the same. A random slope at level 3 only would mean clusters change differently from each other, but everybody from the same cluster changes the same. That would be unusual, I think. What you would typically expect is some blend of, yes, there's something in common because people from the same cluster are going to change relatedly, but everybody still needs their own, even after you control for which cluster is which. So this idea of breaking it up then lends itself into interclass correlations for the intercept and the slope specifically. So once you have a random intercept at level 2 and 3, once you have a random slope at 2 and 3, then you can answer the question of how much commonality there is in each as a function of what cluster they belong to. So this is a level 3 interclass correlation, but it refers to intercept differences specifically and slope differences specifically. So whether you need to control for cluster then is a likelihood ratio test of this numerator and what it contributes to the model. All right, another question from the Zoomers. Nathan, go.
So couldn't you, like, going back to, like, you know, the clusters changing differently, but within cluster being the same?
Yeah.
Couldn't there be a situation where maybe, like, one cluster's rate of change is accelerating, the other cluster's rate of change is linear, and then obviously if you compare, like, within the cluster, they might might be doing the same pattern in change, but then when you compare them, they would be different. Would that be an example?
Acceleration or not would refer to a random quadratic. And if
yeah.
clusters differed in that, that would be yet another variance component.
Oh, okay, because I forgot that you have to add another term
Yeah.
to that.
Yeah, like this
Okay.
is a linear model. This means all you got are lines. Like your only choice is this, right? These are your choices. If you want to allow different forms of change, then you would have to allow that for everybody and then allow individual differences. So like if you had a quadratic model that was bendy, but a certain cluster only wanted to be straight, that would show up as like a positive quadratic, random quadratic that would undo the average and put them back to linear, I think. Yeah, that makes sense. But if you do have quadratics, though, you got to be careful with the linears because they're conditional. Yeah, go ahead.
Well, and I also don't know, like, what real life example would exist for some people would be accelerating and other people's wouldn't. Other people wouldn't, but I don't know.
Oh, well,
Another thing to think
that could
about.
happen. Like you could have some people have acceleration and others don't, and that could be conceptualized as a random quadratic slope, and then that's a variance component you can predict.
Interesting.
Yep.
My brain hurts.
Yeah, mine does too, but I don't know, this stuff is fun. But a general principle though, like when you're questioning your levels, it's like it comes out of the one before it. So you have to have like a detectable random slope variance at level 2 before you would think to say how much of it is level 3. So like if we look at this ICC for a slope, for instance, if everybody from the same cluster changes the same, then this interclass correlation would approach 1, like most of it is cluster. If people from the same cluster have nothing to do with each other in terms of how they change, this would approach 0. I have a note here in terms of like when things are uneven across levels to be careful in your interpretation. So let's say that you have a random intercept, linear slope, and quadratic slope for change over time across people, but you test the random quadratic at level 3 and the likelihood ratio test says, nope, you don't need it. Well, then how you talk about the linear slope is different across levels because it's conditional on time 0 for level 2 via the random quadratic, but it's for every occasion at level 3 without it. So then it doesn't really make sense to do an interclass correlation as much. So in the context of twin data, one of the reasons why people would go to the trouble to collect twin data is to do studies about heritability. To what extent is there commonality in the experience of people with varying degrees of genetic relatedness? So if I thought that there was a strong genetic component to change over time, and I have different individuals from the same family, would I expect this ICC slope to be big or little? If I thought that genetics played a role, big roll and change. And I have multiple people from the same family.
Low?
We got one vote for low. It's a
Are
multiple
you talking
choice
about the
question.
numerator or the whole
Numerator.
thing?
Numerator.
Oh,
So,
then low still.
okay, we got one vote for low. We got a couple votes for big.
Probably like big cluster.
Agree.
Yeah, so if genetics matters, right, then everybody who has the certain genetic type from that family should all change the same. The answer would be big.
Oh,
Yep, good try though. It's 50-50 shot. So in the example that I will show you on Thursday, it actually worked out the opposite way. So among the 80-year-old twin pairs, there was a very strong intraclass correlation for the intercept, but a very weak one for the slope. So heritability studies, by the way, I have an example of those computations because in previous classes I had people who were really interested in this. Twice the difference in interclass correlation between MZ and DZ twins is how you compute heritability in these models. So you can use multi-level models to do genetic decomposition analyses, ACE models or ACED models as they're known. Because yes, everything is a multi-level model, damn it. Even genetic analyses. So you would expect a different interclass correlation for MZ twins and DZ twins if the extent of genetics was contributing to commonality and change. So twice the difference in interclass correlation is how you compute heritability. So that is presupposing that MZ twins will have a higher interclass correlation than DZ twins. And if it doesn't work out that way, heritability can actually go negative, which I have seen happen. And people don't like that, but it's a consequence of the math. So, all right, there. I think that's a good spot to stop. I'll stop on Don's diagram here. 143, any other questions before we call it a Tuesday?
I have an individual question.
Okay, does that mean you want to talk to me now or after class?
After class, it's semi-related but not related.
Okay, fair enough. I will sit here because my next class doesn't start till 16 minutes. All right, thanks for being here, folks. Roomers and Zoomers. We will reconvene on Thursday. Let me know if you need anything until then. Bye for now. Happy garbage day.